Welcome to the South Lyon Area Amateur Radio Club, where passion for radio communication meets community. Connect, explore, join.
I don't know how many of you know me, but Bob W8BK, introduced myself earlier. I'm an electrical engineer by training and was at Ford for 30 years. Um, I also was a ham on, off, and on, starting at age 12, so back in the early 60s. So I've been interested in this hobby basically my whole life. Um, so recently moved from a house where I had a wonderful AV680 vertical, which by the way is for sale, um, that I was able to work the world with, and moved into a condo. Happy wife, happy life. And with the condo, of course, there's no alternative but an attic antenna. So the first thing I did was I sat down and said, what do I want? You know, what are the objectives? And I want HF multi-band capability as much as I can get. Um, I want to be able to broadcast 1.5 kilowatts because I have that capability. It has to be 100% inside the attic. And I want to optimize it for voice on the HF bands. I do some data very infrequently, and I never do CW. I learned at age 11, man's got to know his limitations. Um, and I was hoping to get a radiation maximum in the east-west directions. So we'll see how that all works out. There are a lot of limitations to an attic design, and you got to think about them going in. One is getting the feed line to your shack. Mine happens to be in the basement. Oh, by the way, I have handouts for anybody that wants them later. There's a big risk of foot through the ceiling, and as one who's experienced in this event, uh, and at age 75 or near to 75, I really am not good at hopping from joist to joist anymore up there. The size of the attic, which impacts the length of the antenna, and the height above ground of the attic, which impacts the impedance and the radiation patterns. And we'll talk about that more later. And of course, RFI is also important. I can't upset the neighbors or my wife. And so some of the implications of that are you got to minimize common mode currents on the outside of the shield. They create RFI. There's a radiation effect on appliances, fire alarms, and GFIs. And I have this issue in steroids. The way my house is wired is from the breaker panel, there's a column of Romex about this thick. It runs up the outside wall and then splays across the entire attic. So it provides a secondary ground plane for the antenna. Um, the and lastly, as with all good ham radio operators, we need to stay within the maximum radiation exposure guidelines so that we don't fry ourselves. So I did some prep work before going in, and to address some of those issues. First thing I did was put a catwalk in to prevent falling through or disturbing the insulation as I work on antennas. Because I'm limited to the attic, I expect I'll have to spend more time up there than I want. And so I tried to make it easy for myself. We were doing some remodeling in one bathroom, and there was an area where a wall had to be disturbed. And fortunately, I was able to run a 2-inch PVC pipe through the entire first floor wall into the basement so I could run feed lines down that conduit. I needed some light in the attic, and after having done that by hiring an electrician, I went up after he was done, and of course, all the Romex was run right where I was going to run my antenna. So I had to redo that. And I did some easy neck analysis of the alternatives that are listed below. Those being probably the easiest way to get multi-band capability on HF. And for those of you who don't know, EasyNext's a computer model-based simulation tool for antenna design. Used to cost $650, I know because I paid it. And then the guy who invented it retired and donated it to everyone in the public domain. So you can, if you just Google EasyNet, up will come his website, and you can download EasyNet and then learn how to use it. The antennas we're going to look at are fan dipole, an end-fed half-wave dipole, an off-center fed center-loaded dipole. I hope all of you know what these are, but for those of you who don't, a fan dipole is basically a series of dipoles with a common center feed. And there are some restrictions. The closer the wires are to each other, the more they interact. So you want to try to keep them as far apart as you can. An end fed is basically you take a dipole wire, length half wave, and rather than driving it in the middle, you drive it on the end. And to do that, for those of you who don't know, a dipole wire has a low impedance in the middle, okay, about 50 to 75 ohms. And as you go out towards the end, the impedance gets higher and higher and higher, which means the voltage gets higher and the current gets lower, okay? That's what high impedance means. And typically, the ends are right around 2,500 ohms driving impedance. So you use a 49-to-1 or a 64-to-1 transformer to change the impedance from that 2,500 ohms down to 50 ohms to be able to drive it with your radio. And then there's an off-center fed, center-loaded dipole, kind of like the end fed. Rather than driving it in the middle, you drive it off-center. And there are a couple of different ratios that can be used, and they give you different band alternatives, okay? I will give you some reading or some references that you can go read on the internet if you'd like to learn more about this. And then center loading, what's that? Well, I'll get into that later, I think, because it's complicated. Okay, here is an outline of my house, or it's a condo, but it's really a house because it's a single family dwelling. The garage has a floor on it up in the attic, and I extended a catwalk that went around the basic U shape of my attic. There's also a little turnoff there so that I can get to the wire conduit to run the feed lines down. Turns out the only way I could run an antenna through there relatively straight, and that line's perfectly straight, but my antenna is nowhere near perfectly straight. It kind of weaves a bit, but It's from one corner, which is a hip roof corner, double hip, okay? Means the roof comes all the way down. So it's a small space in there, all the way over to the garage. And again, that's a hip coming down. So I'm sorry? Well, actually, it was right about here. Trying to save a little money by doing the wiring myself. I had to run landscaping wiring to a couple of lamps, long story, but I was installing a transformer up in the attic there, and let's see, the piece of plywood I was laying on it had the perfect storm of two knotholes that lined up. Okay, and I rolled over in between the joists, went through it, went through the ceiling, hit the garage door, which was open, smashed that to, and landed on my wife's car. So, huh? Yeah. Well, $2,000 later for a new garage door and $800 later to repair the ceiling. And I saved a hell of a lot of money. Okay, picture of the catwalk in the attic so you get an idea. You can see it's just a 2-foot path. That's 3/4 inch OSB, which is more than strong enough for even my weight. And after I did that, I had more insulation blown in because this was built in the 80s and there was only about this much insulation in there. Here is the top of the pipe going down to the basement. And it is located, I don't know if you can see right there. There's a piece of wood there, and it's right about over in there. And I have a bat of insulation I install on top of that so that and also insulation in the top and in the bottom so you don't, provide a nice air column of cold air blasting into the basement. I'm sorry? Yes. I know it's not the code. But, when you're running wires through it, it's pretty hard to do anything else. We won't get into that. Okay, one of the issues is as you start to lower an antenna, things start to happen. So, and they happen more on 40 meters than they do on 10 meters. And that's because the wavelength at 40 meters is much longer. It's 40 meters instead of 10 meters. So the percentage of the wavelength becomes much greater at 10 meters and you have less ground effects. But anyway, what happens at 50 feet, 25 feet, and 15 feet, you can see the resonant frequency falls. And as you get closer and closer to ground, funny things start happening because you start putting your nice energy into the ground, okay? The ground starts absorbing energy the closer you get to the ground. And so you see some funny things going on at 15 feet, and that's what it is. Also, you can see the impedance has fallen quite a bit from 375 at 50 feet. And this is on an off-center fed dipole. So you want that to be 200 ohms because you're going to use a 4-in-1 transformer. Elevation, peak, I don't know if Okay, think of a radiation pattern as a squished balloon, if you will. And on 40 meters, you have a really nice balloon. And I'll show you pictures of that later. Very controlled. Because you're close to the ground, the nulls are much smaller than when you're further up. But basically, you have nulls going down the plane of the wire, okay, and two lobes going out. Elevation is looking at it from the side view, and you're at 68 degrees uh, peak elevation, and the 3 dB point down the lobe is at 38 degrees. That gives you an idea of how fat it is, the lobe, whether it's a skinny lobe or a fat lobe. But as you go down to 25 feet and 15 feet, the peak energy is going 90 degrees to the antenna. So essentially, you're broadcasting to outer space. You're warming the clouds, and that energy is kind of wasted. But fortunately, you got big lobes. So you do get some energy, and on 40 meters, the antenna ends up being an NVIS antenna. As you go to 10 meters, you've got all kinds of lobes going on because you got 4 current nodes on the antenna. You can see there's also a slight decrease in resonant frequency and a slight change in the impedance. But again, that change is relatively small because this change, things really start to happen at about a third of a wavelength and less is where things start going south real fast when you're that height from the ground. And you can see that the elevation, while a bit high, is usable. So conclusions: resonant frequency tends to lower, impedance lowers, fundamental radiation patterns shift upward, skyward, and end effect causes the fourth harmonic to be above 4 times, more so at low heights. And I'll get into that more later. Okay, decision considerations in trying to go through evaluating one antennas. First, the dimensions of the attic really preclude an 80-meter antenna without doing some loading. And I did some loading experiments on EasyNet, and I was going to end up with, so little bandwidth, it was hardly worth the work to put the antenna up there. So, and when that happens, you also have radiation efficiency issues. So you pump a lot of power up there, but it turns into heat rather than radio waves. 60 and 30 have limited power and bandwidth, and I didn't pursue those because I'm not really interested in those bands. I definitely am interested in 17 and 12 and possibly 6. But so that gives you kind of, and 40, 20, 15, and 10, the big ones, of course, are of interest. So I explained earlier, we're going to look at those 3 antennas, and they'll be to cover 40, 20, 15, and 10. Because of the low height, none of these antennas will be great for DX, as I said, but each will be more near vertical incidence skywave, which means, it's 40 meters, you can talk around the Great Lakes and some area in Iowa and so on, but you're not going to go to Europe on 40 meters with this antenna. But I'm on the air. Now, I put recent experience in there. Today, on 10 meters, I worked a guy in France. Earlier this week, I worked a guy in Uruguay. Okay, I don't know if you know where Uruguay is, but you know, think Brazil, Argentina. There's a small little country towards the bottom of the South American tip, and he was, I don't, about 5'9". I wasn't struggling to hear him. And I also talked to a guy on 20 meters in Mexico City this week. So the antenna works. Uh, yeah, yeah, 15. Yeah, that's a really good question. And I struggled with that. And so what I did was I did it at 15, I did it at 10, okay, to kind of see what was going to happen. And neither of them predicted very well exactly what was going on, but that didn't mean that the analysis wasn't useful. And I can talk about that later, okay? But that's a really good question. And I struggle with that too. I don't know what to put. Um, the bottom of my attic is only one story up, and the top it varies where you are in the attic. Obviously, in the hips, it's pretty low, but it can be as high as 10 feet up there. So, um, okay, end fed. It's fed from the end. It is an advantage in many applications, but it isn't here because I'd have to put the transformer down in the hip. Okay. And then I have to run a feed line parallel to the radiating line to get to the tube to go in the basement. And that's really not a good idea with an end fit. It has capabilities for the 4 bands. It's a single wire for multiple bands, so at least on the surface, it's not too complex. And it has tuning flexibility with both center loading and loading inductors. And I will get into what that's all about as we go through here. But there are tricks you can play because end effect screws you up on the harmonic relationship of those 4 bands. The cons, some reduction in efficiency versus the other two alternatives because of the un-un. And it requires an impedance matching un-un, which is a transformer. And counterpoise. It's more prone to core saturation at high power and therefore RFI. When you saturate the core of your un-un, you splatter, okay? It's more prone to common mode currents than the other two alternatives, so you end up with a much bigger choke. And end effect requires special tuning considerations for higher bands, i.e. center loading and loading inductors. Fan dipole, the attic's great. It's got lots of wood rafters to hang wires on. Outdoors, this is a con, right? The fact that you got multiple wires. It's hard to figure out how to run string and so on to get them to fan out properly. Center fed helps to minimize common mode currents, but some choke is still required. Cons are a 15 meter presents a tuning challenge and probably requires the use of loading inductors. 15 meters is a multiple of 40 meters. If you try to put a 15-meter wire in addition to a 40-meter wire, you end up with a real low impedance because the 40 is 75 ohms, the 15 is 75 ohms. So the two interact and you end up with about a 30 to 40 ohm driving impedance that you have to do. So you have to use 40 for 15, and then you have to use tuning tricks to get 15 in the right place. For me, feed line must run parallel to the antenna wires. Again, that issue, and that creates common mode currents and detunes the antenna. And interaction between the wires makes tuning challenging, particularly in the constrained space of an attic. It's hard to get them far enough apart. Off-center fed, center loaded antenna, a feed line at 16.3% of the wire will provide 40, 20, 15, and 10 meter bands. If you use a lot, say either a third or 40%, you don't get 15 meters. Or you get it with real high SWR. It has the advantage of a single wire for multiple bands. There's tuning flexibility with center loading and loading inductors. It's got a reduction in efficiency versus a fan dipole because, again, you got an un-un, okay? But it's only a 4-to-1 un-un instead of a 49-to-1 un-un, and there's less loss in that. You also have a large choke. There's some core saturation issues, but not as much as an end-fed. And I used the mother of all un-uns, well, more on that later, to get rid of that problem. There's a smaller choke required versus an end-fed. And again, the end-fed, the end effect on it requires special tuning considerations for higher bands, and I'll get into end effect. Any of these will work. I chose the off-center fed center load. By happenstance, the feed line location was nearest my conduit, and that was totally luck. And that allowed me to take it right off the un-un and down straight, which eliminates a bunch of problems. I read an article by DJ0IP, and that convinced me that I enjoy the tuning challenge. And it was a tuning challenge. I'll go into that. In the future, I expect to design a 17, 12, and possibly 6-meter fan dipole to complete my band portfolio. And I can put it in that, the thing was at an angle, and this part was nothing. So I can put it in that area, and it won't interact with this one. Issues, and this is environmental protection for the un-un. The attic is hot in the summer, but free from precipitation. So I don't have to worry about rain and snow on this antenna, but I do have to worry about heat. And the heat, even with the mother of all balance, you're going to generate heat in your ferrites. And you got to get that heat out of the ferrites, or else the SWR starts creeping up. Fortunately, I used a ferrite that you can't destroy from heat. You destroy the wire before you destroy the ferrite. Finding a straight line was difficult. Matching network and center load mounting can fit anywhere because I got wood all over the place. And the catwalk can't go everywhere. So I still need to take some care when I leave the catwalk to run the wire. And that was a challenge. Okay, when you've got a single wire multi-band antenna, there's a dilemma, and it's called end effect. How many know what the implications of this are? No? Okay, well, turns out 40 meters at 7 megahertz, 14 meters for 20, 21 for 15, and 28 for 10 meters. Boy, they're harmonically related. If I can just get the antenna to work on one, it should on all, right? Wrong. What you find is that if you take 4 on 10 meters as an example, if you take 4 times the fundamental frequency, you would hope that the 4 times whatever you set it at on 40 meters it would end up there on 10 meters, but it doesn't. It actually ends up higher in frequency. So there's this spread of all the bands that you got to deal with. The end effect is approximately 3% of wavelength, but this varies depending on the height of the antenna and other factors such as your ground conductivity. And hopefully the next slide will help you with this a bit. Right here is a sketch of a wire and the current nodes that occur on that wire when you excite it with RF energy. Okay, so at 40 meters, you get one big current node that goes across the whole wire. At 20, you get two. 15, you get three. And 10 meters, you get four. Well, so far, so good. 4 times should work, right? Well, hopefully you learned when you took your novice test that to make a half-wave dipole, the formula is 468 divided by the feet in megahertz. Everyone remember that one? Okay, well, there's another formula called a half wave is really 492 divided by the frequency in feet. And what that is the electrical length of the actual wave that gets produced off the wire. Okay, it's actually a bit longer. And there's a 5% difference in that. And that 5% is made up of 2, potentially 3 factors. First one is the velocity factor of the wire that's being used. Turns out the speed of light in air isn't the same as the speed of light in a piece of metal. It's slightly slower in a piece of metal, okay? So there's a factor you have to multiply everything by, and just bare wire is 2%, okay? Then the end effect is 3, and in the next slide, I'll explain a little better what end effect is. Let's compare 40 meters to 10 meters. It's got the biggest difference, so it helps to understand it. 10 meters has 4 current nodes, and those 4 current nodes have 8 minima. There's 1, 2, 3. Oh, that's the wrong one. 1, 2, 3, 4, 5, 6, 7, 8. Okay, but only 2 are at the end of the wire. 40 meters has 1 current node with 2 minima and 2 ends. Okay, so it turns out the 3% reduction goes across the entire length of the 40 meter. So you cut a 40 meter wire 3% shorter to account for end effect going in, okay? However, when you get to 10 meters, you only got these 2 little ends here that are being multiplied or reduced by the 3%, okay? So in order for all of this shortening that occurred on 40 meters applied to here, the only way you can get that 4 nodes shorter is if the wavelength of the 10-meter wave is shorter. Okay? And when the wavelength's shorter, the frequency is higher. So instead of being 4 times, you're 4 times plus some factor that is the result of the fact that the 10-meter wave on that wire only sees a small amount of shortening from end effect. Does that make sense to everyone? Okay, standing wave ratios. A lot of misunderstanding about standing wave ratios, so I thought I'd spend just a minute on it. An objective in designing antennas to minimize the standing wave ratio. And the standing wave ratio is a metric of how well an antenna, a feed line, and the radio are matched together. And typically, they should be 50 ohms. When an antenna system is perfectly matched, that means the three of those, the maximum amount of energy is transferred from the transmitter to the antenna, okay? And conversely, from the antenna to a receiver when you're listening, you get the best transfer of energy. If the feed line system, or if the antenna system has an SWR greater than 1:1, you can use a tuner to match the antenna feed line to your radio, and this protects the radio. However, you still have losses in the tuner, the feed line, and the antenna. And that energy loss creates heat rather than radio waves. So the best antennas are resonant and have a low SWR and do not need tuners. However, you know, if you got to use a tuner-based antenna system to get on the air, it's certainly better than no antenna at all. So just realize that there's some compromise you're making by doing that. The best answer is to be resonant and not use a tuner. Next slide will explain how to tune this antenna to minimize the need for a tuner. I found an interesting article in CQ, May 2021, by these two gentlemen that talks about the off-center fed dipole. And summarizing part of what they learned in doing it is, what tuning levers do you have for this antenna? Meaning, what can you change to improve it to matching its use where you want it to be? You can use the length of the wire, and that kind of moves everything together, right? You can change the feed point location from 16.3. Some books will tell you the answer is 16.4 or 16.5 or 16.2. It's somewhere around there. And the right answer depends on what your environment is, okay? But it's somewhere right around there to get those 4 bands. Center loading is putting an impedance, either an inductance or a capacitance. Said another way, a reactance, which is the imaginary part of impedance, in the center of the antenna. But you can move that location, and I'll explain why you might want to. And if it's exactly in the center, you have an SWR minimum frequency on 20 meters. Okay, if you remember, there's 2 lobes. And if you stick a load on the antenna right in the middle, there's no current going through the center of the antenna if you're broadcasting on 20 meters. So guess what? There's no effect from that load that you put in the middle. That's also true on 10 meters. Okay, on 15 meters, you get some effect, but you have to remember reactance is a function of frequency. Okay, so if you have a reactance at 40 meters, you get 1/4 of the reactance on 10 meters because it's proportional to the frequency, okay, with the same component. Maybe a little bit too much into the weeds, I don't know. Anyway, your tuning approach for this antenna. Set up the antenna length based on 20, 15, and 10. Okay, don't set it up for 40 meters. You'll end up with a 40-meter resonance around 6.6 to 6.8 megahertz below the band. modify the feed point to optimize the software, the SWR trade-off between 20 and 15. As you move back and forth from 16.3, you'll see 20 and 15 move back and forth. Okay. Establish a center load capacitance to move the SWR response of 40 meters. If you put a capacitor in the middle of the antenna, it will shift the 40-meter frequency response to the right. And you can, by changing the amount of that capacitance, put it right on top of the 40 meters or the top of it or whatever you want. And then tweak the center load percentage to fine tune the band locations. I say this requires easy neck. I did it through simulation because once you cut the 40% wire, you don't want to be replacing wire and checking 38 and 42 and 44%, right? That's a big pain in the butt. So I did it with simulation. It turns out I got about 40%. It turns out those two guys got 39%. So it's going to be somewhere right around there. And if it isn't perfect, well, this is what I ended up with. A half wavelength, and it was resonated at 6.6 megahertz without the center load installed. And that ended up being, I can't remember exactly, it was something like 66 feet and 3.5 inches or something like that. I ended up with the center load at 40% and a 15 picofarad capacitor. And you put a very high resistance resistor across that, so you don't get static buildup across that capacitor and break down the capacitor. That's what that's there for. A voltage balun that converted the 200 ohms to 50 ohms, and big old common mode choke. Okay. And red shows where the response came out. This is after tuning, before I added the center load. And with the green, you can see I shifted the peak over on 40 meters in right here. It turned out it moved on 20 meters a little bit. And that's because you're starting to go up the side of that node. Okay, and now you got some current. It didn't impact 15 hardly at all. And I'm not quite sure why, but it impacted 10 meters quite a bit. And I think that's also because the 10 meter, you got 4 of them. So the slope near the center is really quite high. And so when you move in 40%, you're pushing up close to the peak of the first 10 meter hump away from the, does that make sense? Okay. Just so you don't think it's all a piece of cake, this was my first try. And you can see this is almost at what, 6 megahertz. This is clearly below 14. This is clearly below 21. And this one doesn't look like it has a hope of ever hitting 10. But little tuning and we were good. Here's an appendix. In it, I've put some other information on the transformer looks like. Okay, and it's a Ruth-Roth voltage balun is what it's called. But basically, it's just an auto transformer, a 2-to-1, a 4-to-1 transformer, but the windings here are equal, right? The windings are 2-to-1, and the impedance change is to the square of n. So 2-to-1 gives you a 4-to-1 impedance change. And then common mode chokes going to the 50 ohm output. The common mode chokes are to stop common mode currents from rushing down the feed line. Here's what the thing actually looks like. This is from the article in CQ, what he had. You can see two number 61 2.4-inch toroids, and it had 14 turns of magnet wire with a Teflon sleeve. I used silver-plated Teflon coated wire on mine. But you'll see something that's different. If you look at this, you got two toroids that are 1/2 inch. I bought these and they were 3/4 inch. Okay. They were 2.4. They were the same diameter, but they ended up being higher. So I have the equivalent of 3 of these sitting over here. Well, that created some problems because that shifts the response of the balun. And so I had to change the number of turns of windings. Okay. I changed it so that I basically took 1 off the primary, 2 off the secondary, which means taking 1 off the bottom part and 1 off the top part. Okay. All this was done long before it was in the attic. The attic's the last place you go. This is the frequency response of that balun with a 200 ohm resistor as an antenna. And you can see blue is the resistance, red is the impedance, and green is the reactance. You can see the reactance starting to come up here. And this is what killed me the first time through, where I had to take the windings out because the reactance got much higher. And that started to change the impedance up around 10 meters. So taking some windings out fixed that. And you'll see that it goes all the way down to about 160 meters. One other thing I did was I put a balun at my linear and in the shack. And the reason why is I'm running that wire down the conduit, the cable, the LMR 400, down that pipe, and it's only 6 feet away from my internet modem and about 2 feet away from a switch, an internet switch, which is switching between. And so there's all kinds of hash coming out of that. Okay. And also LED lighting creates a lot of hash. Okay. By putting this here, it isolates the outside of the shield on the feed line from injecting any noise currents into the ground plane of the amplifier. Okay, if you put a noise current into the ground plane of the amplifier, the inside of the coax is steady, right? And this is moving. So you have a differential current. And that noise comes through in your receiver. So this is one way to effectively deal with that. That provides about 5K, 4 to 5K of impedance through across that band we were looking. The one on the balun in the attic provided about 8 to 10K, which is a lot of isolation. I think why is isolation needed? Everyone knows the coax cable has 3 wires, right? Inside wire, inside of the shield, and the outside of the shield. The inside and outside of the shield act totally independent from each other because of the skin effect of AC at RF. Okay? There could be an insulator in the middle of the shield, and it wouldn't act any different. So the outside of the shield acts as a separate conductor, and you need to deal with that. That's why when I talk about antennas, it isn't whether or not you need a balun. You need a balun. You always need a choke on a wire antenna. Always need one. If you don't want common mode currents. If you want all the current to radiate from your antenna and not come down the cable and interfere with your neighbors and wife and everything else. Second is the center load. I use two doorknob capacitors. In case you don't know what they are, they're high current, high voltage transmitting capacitors because there's a lot of current going through them. Capacitors are not just capacitors. They have inductance and they have resistance. And the thing that you're concerned about in this kind of a environment is all capacitors have series resistance. If you're passing a lot of current through a capacitor, you get I squared R losses. You get current heat generated to the tune of the square of the current times the equivalent series resistance. So you can generate a lot of heat in a capacitor if you're passing large amounts of currents through it and blow it up. So you need the right kind. Also, there's a adjustable air gap. You can see it's got really big air gaps. It's a 7 to 57 picofarad adjustable capacitor. And if I want to shift that 7-meter response around, all I got to do is go in the attic and rotate that baby a little bit, add a little capacitance or take some out, depending on which way I want to shift it. Here's a suggested reading list for you if you want to understand more about this antenna and other types of antennas like this. And here's the balun information. Radiation patterns. This is the radiation pattern. The wire in their model simulations, because it's really hard to go out and measure your radiation pattern. Takes a lot of measurements. But anyway, the wire goes down the axis of the x-axis, negative and positive, okay? And you'll see a little dissymmetry, and that dissymmetry is a result of the fact that you're not feeding in the center, you're feeding it off center. So it affects it a bit. But you can see there are essentially two lobes going out this direction. And the null in the middle is quite a bit less than you probably thought there should be for a dipole antenna. And that's because it's close to the ground. Okay, radiation pattern at 20 meters. Okay, you end up with 4 essential lobes, 1, 2, 3, and 4. And they're more symmetric than this thing looks in reality, okay? Again, the nulls here and here are not very distinct, but they are in the direction of, perpendicular to the antenna itself. So this radiates a little better down the axis of the antenna than it does the other way. Okay, this is at 15 meters. You end up with 6 lobes, actually 7. You start getting this nasty one in the middle that's sending energy straight up and will be picked up by aliens someday in another universe. But you can see you're getting energy out in just about all the directions. And again, the nulls are getting a little better defined. You can see them a little better. And on 10 meters, where you got those 4 current nodes, you end up with, well, primary 8 going around the bottom. And I think there's 3 or 4 of them up, coming up, sending energy to outer space, okay? But like I said, I worked Mexico City and Uruguay on these side lobes. Okay. Here's the final frequency response on 40. You can see I biased it towards the single sideband end of the band, but it's real easy for me to shift that over if I want. But you can see I'm under 2.4 across the entire band. And in the region I want to be in, I'm well under 2. 20 meters, look at that. 15 meters, again, under 2.0 across the whole band. Most of my action is up in this area, up 10 meters, 28.5 I was able to get up to for the minimum SWR. And you can see that across the entire band, I'm under 2, which shocked me. Okay, now, boy, these are good. Boy, these are close. What's going on? Why is this so good? The answer is because it's so low to the ground, I'm putting all this energy into the ground, heating the earth. Okay, so while it looks good, okay, I'm paying a penalty because it's so close to the ground. So that's it. Any questions?
The shift in those frequencies was all due to the center loading that you put on?
In that one chart with the red and the green. Yes.
But with the shift of the frequency stuff too, right? Yeah, with the red and the green. Yeah, that moves all that. Yeah, that one.
That one. Yes. That is the effect of the center load and nothing else.
Okay.
Okay. Yes.
You said in the beginning that your line was not straight,
Correct.
but then, so how much difference is if it's perfectly straight or if it's the way the or curves or the
Okay. All right. In the center, it's up quite a bit, up to the ceiling. And it's like that in the load, and it goes through, and then it starts going down a hip. Okay. And the corner, where is it? This corner here ends up being more like this, you know, it's not perfectly straight. And you've got a hip here and a hip here. So the antenna is going way down with the roof. Okay. But if there's any part of the antenna you want low, it's the ends. Okay. Well, yeah, kind of. Yeah.
you and family is going to get kilowatts to be exists.
Well, if you work through the analysis, it's also dependent upon the amount of time of exposure. It's not just related to, you know, that instant of time. Okay. So when with my gear, I can adjust, I have infinite adjustment of the power output of my system. Okay. And what I tend to do is go in at low power, depending on what you know, how strong the signal is I'm talking to. Okay. And where it is, I might go in at 100 or 200 watts. Okay. And if they're having a hard time hearing me, I'll juice it up until I'm okay. And yeah, I get an occasional fire alarm go off. And, you know, with all that Romex running around in my attic, it's virtually impossible not to get RF feeding right down into an appliance. My wife's clock on her nightstand gets reset every time I transmit. And she loves that. I gotta buy her a new clock. Yeah, it starts at 0 again. Yeah. Uh-huh.
L shape, one corner.
The answer is yes. But the issue is how well. Okay. If it's an L, you'll tend to get a load that goes out in the, between the 90-degree part of it. Well, if it's fiberglass insulation, it doesn't care, or paper. Okay. The radio waves go right through that. They don't even see it. Okay. If you've got metal, if you got an aluminum roof, you're done. Okay. You're not putting an antenna in the attic. Yeah. Aluminum siding is a problem if you're inside the house, but you know, um,
I had a new put on like 4 or 5 years ago.
yeah.
And I vaguely remember the company that installed, it's asphalt shingles, but they're like, you get more money to have slightly better ones. And he said to me, he goes, do you have any antennas? And I wasn't a ham operator that. I said, no. But I don't know why he asked me that question. It's just asphalt shingles, so that
Shouldn't be a problem.
They do make in certain homes, there's board they put up there that is an aluminum layer.
It has a foil layer on it.
Foil layer for insul. No, it was a thermal barrier.
Well, yeah. Should be an interesting experiment.
Yeah.
Hopefully you don't get eddy currents that cause it to heat up.